Can you close the door? Okay, so did you come up with any questions? So your favorite numbers?
Before favorite numbers, page
Okay, great.
127.
Page?
127 of the book. Equation.
Equation?
After equation 28, we say note that the limiting distribution 28 is precisely one expected of an oscillator in its ground state. So I could not calculate this one, this oscillator in ground state, and match it with that one.
Okay, so what is it doing? Can you explain to your friends? So in which section are we looking at now? Yeah. So what does it do?
To be honest, I forgot which part of discussion was that. I just remember that I could not relate this to the distribution of the ground state of the oscillator. Can we go on?
Well, let's see. Let's suppose you want to calculate the density matrix for the harmonic oscillator. What do you do? How do you calculate this? You are given this question. How do you proceed? Okay, the Hamiltonian is this one. Let's do the one-dimensional case. Okay, this is the Hamiltonian. Now what?
I think we need to establish a basis. Basis.
Okay, which basis do you propose?
So we want to calculate with R states, right?
Mm-hmm.
States corresponding to R. And we can find the eigenstates.
Eigenstates of what? Okay, the eigenstates of the Hamiltonian. Well, we already know the eigenvalues. So it's h bar omega n plus 1 over 2 psi n. So you solved it. Psi n's are known functions. Or if you like, hn. H bar omega n plus 1 over 2 n. By the way, how are these states n and psi n of R are related? What's the relation between these two notations? We sometimes use the Bryan-Ket notation, we sometimes use the wave function. What's the relation between them?
Basis.
Hmm?
Just the basis. The right one is the coefficients of the state in position basis.
So you are saying that n is actually integral of, you mean this one? Okay, so what do you mean?
So psi and r.
You need bra.
Where? Here,
No, to the right side.
to the right hand side.
No, I mean that's.
Okay, so what's the relation between the ket and the wave function?
Also, phi n's here are bra of r and ket of n. Yes.
Okay. So this is also correct.
Nice.
You see, what you do is n is just r, r, dr, n. Because the eigenkets of the position vector operator, it's also a complete set. So, and this is psi n of r. Okay, so back to our initial question. We are asked to calculate this quantity. We are interested in this quantity for some reason. So we know the Hamiltonian. We found the eigenbases and the eigenvectors and the eigenvalues. Now what? How do you proceed with that knowledge?
Calculate the integral is
Which ones? I don't see any in my expression yet.
same way we translated the bracket production into the multiplication into integration. Same thing over here.
You mean here? But here I inserted this identity in terms of the position basis. Do you propose we do the same thing here?
We insert two identities. We want.
Well, let's start with one of them. So where should I insert? I mean, you want to insert this identity, right?
Between
One.
the operator and the kits if you want.
So this is the identity you want to insert, right?
I want to insert this one.
Well, let's see what this one will tell me.
If I inserted this one, thing another. But if I inserted the eigenvalues of the Hamiltonian,
Eigenvectors, you mean?
eigenvectors of the Hamiltonian, but then the integration would have to run over E, right?
Is that integration? If I use the eigenvectors of the Hamiltonian.
Sum and that.
The eigenvalues will be discrete, so it's a summation. So you are proposing we should insert this identity. Do you agree with him that the first identity will not give us any result? You see, both of these identities are correct. We can use any one of them. So what happens if we use the first one?
No, nothing changes.
What do you mean nothing changes?
You have R, ion, ket.
And the Hamiltonian does not commute with the first one.
So it's not a requirement. I can use any basis to express
It's
one.
much easier when
Sure.
we use hands.
Yes, I inserted this identity. What is this matrix element?
It's a function.
It's a delta function.
It's satisfactory of the starting point.
Now I can just evaluate the r double prime integral. So this is just r prime e to power minus beta h r. So back to the initial point. That's why the first identity, resolution of identity, doesn't really give me anything new. I can try the second one. Well, let's try the second one. There's a summation over n. Now I can simplify this one a bit. You say this one, Hamiltonian acting on n, just gives me the energy. So it will be e to power minus beta En. But you had already said that this is nothing but psi n, the wave function. And this is its conjugate. So now I have this summation. So this is an identity we have. We don't really know what the summation is. Let's say from 0 to infinity. But already from this approximation we can derive certain results. Let's say, let's shift the Hamiltonian such that H0, Hn is h bar omega n. I just ignore the 0-point energy. I just shift my potential energy if you like. I can always shift my potential energies. Now, what happens to e to power minus beta En as beta goes to 0? Sorry, t goes to 0. Remember, beta is 1 over t. So as t goes to 0, what happens to beta? Beta goes to infinity. E to power minus infinity En's are either 0 or positive. If En is positive, then it's just e to power minus infinity, which is 0 for n, 1, etc. But if n is 0, En is already 0. So e to power minus beta En before taking the limit, it's already 1. And it stays 1. So what do we know is, if we consider this matrix element, if we take the limit t goes to 0, well, it just gives me only the n is equal to 0 term survives in this summation, and that is psi 0 r prime psi 0 star of r. Well, you see, up to this point, it's just some trivial observation, let's say. But you see, at the left-hand side, that matrix elements, we don't have to use this identity. We don't have to use this identity to evaluate the matrix element on the left-hand side. There are other tricks, other methods, other numerical methods to evaluate this matrix element over here. But what this tells me is, if I somehow manage to calculate the left-hand side, either analytically or numerically, then take t very small or beta large enough. If it's a numerical method, I cannot just take beta to infinity, but I can assume it's a large number. If it's a large number, well, that matrix element just gives me the wave function, the two products of the wave function at different points. If I choose r and r prime to be equal, well, if I just set, sorry, not equal to, t goes to 0. If I take the low temperature limit, if I calculate the left-hand side by some other means rather than using the eigen functions, well, from that knowledge, I can calculate the wave function. Well, in fact, what is usually done is, if you look at this function, if t is much, much smaller than, let's say, 1, much, much smaller than some characteristic temperature, let's say, it goes to 0, then this matrix element will be just e to power minus beta E0 psi 0 of r. Now, if E0, let's say, if the ground state energy, if it's not 1, if it's not 0, well, by just looking at how this changes as a function of beta, as you change the temperature at very low values, but if you just look how that expression changes as you change the temperature, you can determine the ground state energy of your system. Well, this is commonly used in what's called the lattice field theory. We can calculate the left-hand side using Feynman's path integrals on the computers numerically, whatever the value of beta is. Then using that knowledge, we can determine the energy eigenvalues for a given system numerically. The ground state energy eigenvalue. And the wave function of the ground state. You see, that is what is given over here. It just evaluates, I will not go into the details, the beta, the QQ prime, this is RR prime, density matrix, this is the result. Then it just takes the limit, various limits. You see, if t goes to 0, you see, in this case, T0, the characteristic temperature is actually h bar omega over k. This is the characteristic frequency for this system. If the temperature is much lower than the energy required to excite the state, you see what's actually happening over here is you have the harmonic oscillator. It has discrete energy values. The separation between two energy values is given by h bar omega. Now, if the temperature of your system is such that kT, the thermal energy, is below that h bar omega, it goes to 0. So you have these oscillators, even if they collide with each other, you will not be able to excite them. So they will all go to the ground state. So here in the low temperature limit, the diagonal elements of the density matrix just turns out to have this form, but this is nothing but the ground state wave function of the harmonic oscillator squared. That is what is meant over here. It's just phi 0 squared, this function. Okay, there were some questions about thermal wavelength for a given system. What's the thermal wavelength? Do you remember? Do you remember what it means? Okay, so let me ask you this question. What is the average kinetic energy of a particle if the system has a temperature T? If it's an ideal gas, it's typically 3 over... No, even if it's not an ideal gas, the kinetic energy is always 3 over 2 kT. So this is the average kinetic energy, which is P squared over 2m. So what's...
You can fit that with h omega and reduce the frequency or the wavelength.
P is equal to 3m kT square root, and the corresponding de Broglie wavelength is h over p, which is h over 3m kT. This is not exactly the thermal wavelength, but sufficiently close. It is a typical, you can just say that it's a typical de Broglie wavelength of your system. Typically, they will have momentum around this value, and hence your particle will have wavelength around this value. Why is the de Broglie wavelength important?
It tells us the system can be behaved not mechanically or classically.
How does it tell us?
For example, the system
You see, this is typical distances over which quantum mechanical effects become important. So if you are I don't know, if you, let's say, if you are colliding two particles and their average separation, their minimum separation is smaller than this number, then you have to treat the system quantum mechanically. Classical approximation need not give you the correct answer. But as your friend pointed out, if you have your system such that the average separation between the particles is less than the de Broglie wavelength, then quantum mechanical effects will be important. If the average separation is larger than the de Broglie wavelength, then the quantum effects will be negligible. So that also tells us the limit in which the ideal gas equation will be correct or false. You see, what is the average? Suppose you have n particle in a volume V. What is the typical separation between them? V over n? Cube root. This is the typical separation between the particles. So if this number is, let's say, around the thermal de Broglie wavelength, then you know that you cannot treat your system as an ideal gas, classical ideal gas. You should definitely treat it as a quantum mechanical system. And in fact, this tells me that the ideal gas equation might be valid if, let's say, this is V over n to the power 1/3 times t to the power 1/2 is much, much larger than, let me put 1. It's not 1, but that ratio should be very large. Or this also tells me that V over n times t to the power 3/2 is large. You see, I probably remember, ideal gas law is valid for if the gases are rarefied, they are not dense. But that just basically means that V over n is large. Or at large temperatures. Well, that just means that T over here is large. What is actually the condition is that V over n times t to the power 3/2 should be large. It can be, V over n can be small. It's not so dilute, but T can be large. That's also a limit in which the ideal gas law will hold, ignoring interactions. But if V over n is small, the density is high, if the temperature is low, well, you cannot avoid the quantum mechanical effects. And what I mean by the quantum mechanical effects will be, you see, ideal gas law is valid when we can ignore the potential between them. But quantum mechanical nature of the particles creates some kind of an effective potential. You see, if you remember, the effective potential between fermions is repulsive, so that its density matrix, when the separation between the particles is 0, is small. The density matrix is not uniform in coordinate space. So, which basically tells us that the fermions, effectively, they will repel each other. Okay, I say effectively they will repel, there is no force acting, they are not exerting any force on each other. And bosons will attract each other, effectively attract each other. And I repeat, there is no attraction between them. There is no force attracting them. And that was the discussion on the effective potential. This is the statistical potential between for the fermions and bosons. You see, for fermions at small distances, the effective potential just repels them. And for bosons, it's attractive. And in both cases, when the distance is comparable to lambda or larger than lambda, these forces become negligible. Other questions before asking your favorite number? Yes, there is a question on that corner.
No, you have answered all those questions today.
Okay.
Maybe we can solve a problem which enclosing our all of the
Okay, that's why I want to ask your favorite number.
maybe we can say number in the middle of the problems.
In the middle. Okay.
The first problems are 1, 2.
Well, there are not many problems anyway, so let's see. Question 5. Let's start with 4. Okay, question 5 will take a bit long time. So I said that calculate the density matrix for unsymmetrized wave functions instead of the symmetrized wave functions. Show that following this procedure, one encounters neither the Gibbs correction factor nor a spatial correlation among the particles. Okay. So let's stick with 2 particles. Do we get this 1 over 2 factorial or not? Or any effective potential between them. So we are calculating this 1R1, R2, e to power minus beta h, R1, R2. The Hamiltonian is P1 squared over 2m, P2 squared over 2m. All of them are operators. Well, the eigenfunctions of this system are, one particle has a momentum P1, the other particle has a momentum P2. These are the eigenvalues of the momentum operators for each particle, e to power I P1 times R1 plus I P2 times R2. We are in a volume V, so the normalization is 1 over square root of V. This is the wave function I have. Now, if I had a fermions or bosons, you see this is actually P1, P2, R1, R2. If they were identical fermions or identical bosons, I would have this wave function. The wave function of my system would have been 1 over square root of V, square root of 2V, e to power I P1 times R1 plus I P2 times R2 plus or minus e to power minus I P1 times R1, no, plus P1 times R2 plus I P2 times R1. You see, if I take the plus sign, it's symmetric under the exchange of R1, R2. If I take the minus sign, it's anti-symmetric under that exchange. Also, there was another question about how is the spin of the particle related with the statistics used in your pre-reports. Well, I wouldn't go, I mean, in field theory at least, what you can show is if you have fractional spin particles like spin 1/2, spin 3/2, etc., the theory you write doesn't make any sense. So, so that's why for those particles you say that they have to be, okay, the theory doesn't make sense unless you assume that they anti-commute. They should anti-commute if the theory, for the theory to make sense, which basically corresponds to them being fermions. So if you have fractional spins, they are fermions. If you have integer spins, they are bosons. There is the spin statistic theorem which proves that this theorem also is valid if you are not in 2 dimensions. In 2 dimensions, this theorem is not valid. So we have all these, if you are interested, anyons. They are neither fermions nor bosons, but they can only exist in 2 dimensions, not in other dimensions. Okay, so in this question, what it says is, don't symmetrize or anti-symmetrize your wave function. Just use this non-symmetrized forms and see what the density matrix looks like. Okay, I know the wave function, so let's go back and write this matrix element. Well, this will be equal to, I have a summation over all the momenta, P1, P2. Well, since I have the Hamiltonian over here, I use the eigenvalues of the Hamiltonian, which will simplify my computation. So it's just P1, P2. Then I have R1, R2, e to power minus beta h, P1, P2, and P1, P2. R1, R2. I'm looking at the diagonal entries, which will be equal to P1, P2. Well, e to power minus beta h with momenta P1 and P2. That is just Hamiltonian acting on this state. And here I have 1 over V. This matrix element just gives me the wave function e to power I P1 R1 plus I P2 R2. This one just gives me its conjugate, e to power minus I P1 R1 plus I P2 R2. Well, if I just multiply these two, they just cancel each other, it's just 1. So R1, R2, e to power minus beta h, R1, R2. It's just P1 and P2, e to power minus beta, P1 squared over 2m, e to power minus beta, P2 squared over 2m. Well, this is just actually sum over P1, e to power minus beta, P1 squared over 2m, or let's say just P. This whole thing squared. You see, there is no position dependence. In fact, if you write the actual density matrix, R1, R2, classically, this should be actually equal to the density of particles at the point R1 multiplied by the density of the particles at the point R2. This will be just this number. So there's a over V over here. squared 1 over v divided by, well, the normalization. And the normalization would be if I integrate this over r1 and r2, you see, d cubed r1, d cubed r2, rho r1, r2, they should be equal to 1. This is a normalization. Well, to have that, here I should have 1 over v squared. Well, okay. Let's say some normalization over here. And you see, nothing depends on r over here. So rho r1, r2 just turns out to be 1 over the volume squared. So there's a uniform density. That is what we would expect from classical physics, the density of particles. If we have two particles, their probability density of being anywhere should be just uniform. But quantum mechanics, due to their fermionic or bosonic property, which reflects in the symmetrization or anti-symmetrization of the wave function, shows us that the density of states will not be uniform. The probability of having two fermions or two bosons at the same point or close to each other will be different than the probability of, or the density of observing them far away from each other. Yes?
Why don't we have primed coordinates?
Well, you see, we talked about the density matrix. We said that rho and m can be actually given as pi, ani, am, star I, where we are saying that my system is in this state an, psi, and I with a probability pi, ani. Sorry. If my system is in this state with a probability pi, then this is my probability density. What is the diagonal elements? Rho n, pi, an, average squared. Now this is the probability that my particle is, if my particle is in this state with I, the probability that it will be in the nth state. I will measure it in the nth state. So I'm just taking over the ensemble average in general. So this, in a sense, this is the average probability, the diagonal elements. Now, if I want to find the density of particles, well, the density of particles is essentially the probability of finding my particle at a given point. So if the probability that I will find all my particles at this point is 1, then the density here will be huge, and the density everywhere else will be 0. So what I am interested in, if I'm interested in the density of my particles, that means I'm interested in the diagonal matrix elements of my density matrix in the position basis, because I want to calculate the probability of observing them at this point over here. That's why I take the diagonal entries.
But if you want to find the value of some observable, we need the whole density.
Sure. You need the whole observable. In that case, you have to put r primes over here, r1 prime and r2 prime. Then you will be calculating all of the density matrix elements, not just the diagonal ones. Anything else that we should do in this question 4? You see, there is no 1 over n factorial. It didn't appear anywhere. No special correlation among the particles. The position of one doesn't affect the position of the other one.
We said that the density matrix in this form
what we said is the diagonal elements of the density matrix corresponds to probabilities.
So, is there any way we can interpret all diagonals in any physical way? Or
Not really. I mean, they will cause interference effects. You see, for example, in the book, when you were proving that the density matrix is diagonal in energy basis, you also assume that the average of e to power I theta n minus theta m, this was just 0. This was an assumption. Which sometimes also said that the state is an incoherent collection of these particles. The phases of different particles are arbitrary, they are random in a sense. Since they are random, that exponential over here, when you are taking the statistical average, it can be positive, it can be negative, it can be pointing in one direction in the complex phase space, or it can be pointing in just the opposite direction. So the average just turns out to be 0. Yes, other questions? So then see you next week. See you on Monday.